Alright, hopefully this lecture's on the shorter side. So we're going over even more gas laws. There's just two that we're going to cover. We're going to cover Dalton's law of partial pressures, and we're going to go over Graham's law. These should be kind of fun because they're a little break from the typical fraction-like material that you're working with the other gas laws. Also, people speculated that that guy had red-green color blindness. Alright, so just a quick couple of notes before we really get into Dalton's law. A couple of things to keep in mind. Dalton's law has to deal with mixtures. And the general idea is that, let's say we have a container that has a mixture of gases. The particles in a gas mixture at the same temperature, they have the same average kinetic energy. So really, the gas pressure only depends on the number of gas particles in this specific volume and on their average kinetic energy. So the kind of particle that it is actually doesn't matter at all. Each particle makes the same contribution to the pressure of the mixture. So if you know the pressure of each gas, then you can find the total pressure of the mixture by adding up all the pressures of each gas, called partial pressures. And partial pressures are represented like this. If you had a mixture and it had oxygen in it, and you wanted to find the pressure that's coming from oxygen, the partial pressure of oxygen is written like this. So you got a P telling you pressure, but now you have subscript O2. If it had argon in it, you would put pressure, subscript argon. That tells you partial pressure. So this equation right here is the equation for Dalton's law of partial pressure. So the idea is that the total pressure of a mixture is equal to the partial pressure of your first gas plus the partial pressure of your second plus however many gases there are in that mixture. So let's just say we had a sample of air, and the units that we're using are kilopascals. And these were the samples that we had. We had one sample of oxygen, and that had a partial pressure of 20.9. We had another sample of nitrogen, and that had a pressure of 78.1 kilopascals. We have argon, 0.97, the rest. If we took these 5 gases, or if these were the 5 gases that were in the sample, we placed them all in the same volume, then what would the total pressure read? Well, hopefully it's pretty simple. You just have to add them up. And in this case, it comes out to 101.3 kilopascals. How convenient, since this is a sample of air. Alright, now that's a pretty easy problem. Let's try another one. So here it says, in the chem lab, a student filled a balloon with 2 different gases, CO2 and N2. The atmospheric pressure in the lab was 770.0 milliliters of mercury, and the partial pressure of CO2 added to the balloon was 0.3255 atmosphere. What was the partial pressure of N2? So we have a balloon, and in it we have carbon dioxide and N2. We know that the total pressure is 770.0 millimeters of mercury, and we know one of the partial pressures. We know that the partial pressure of CO2 was 0.3255 atmosphere. And the question is, what is the partial pressure of nitrogen? Well, if we turn to our equation, we know that the total pressure of this system is going to be the sum of those 2 partial pressures. We already know one, we just need to find the other, and we know the total pressure. And this question wants us to fall for the silly mistake. These units are not the same. And they must be if we're going to solve it correctly. So you get to make a choice. Millimeters of mercury or atmospheres. It literally doesn't matter. I don't care what you pick. But I want you to pick atmosphere. So let's go ahead and convert the total pressures units to atmosphere. We know that we have 770.0 millimeters of mercury. What is the relationship between millimeters of mercury and atmosphere. Very good. 1 atmosphere is 760 millimeters of mercury. So that should come out really close to 1. So that comes out to 1.013 atmosphere. So we know that this is the total pressure. So we know that 1.013 atmosphere is equal to 0.3255 atmosphere plus the partial pressure of nitrogen. So we just have to solve. So hopefully you know that you can just take the total pressure and subtract a partial pressure. And since we only have 2 gases, we know that the pressure that we get left over is going to be the partial pressure of nitrogen. So 1.013 minus 0.3255 comes out to 0.688 atmosphere. That is the partial pressure of nitrogen. And I know what you're thinking. Sir, that's too easy. Give me another problem. Okay. Alright, so in this problem it says, in a lab experiment which was done with a barometric pressure of 1.043 atmosphere, some H2 was collected over water at 27 degrees Celsius. What is the partial pressure of the dry H2 in the container? So in this case, we have a measurement of the total pressure, which comes out to 1.043. So we know that. And we're looking for the partial pressure of hydrogen. And it doesn't give us another pressure, but it does tell us that H2 was collected over water at 27 degrees Celsius. And then it says, what's the partial pressure of the dry H2? What that implies is that there's also water vapor present, which shouldn't be too horrifying for you. Remember when we learned about thermodynamics and states of matter, that water is going to be evaporating at any temperature, right? So at any temperature, you have water molecules creating a vapor pressure. So water vapor will go into the atmosphere, and it turns out, remember, it's respective to temperature. At different temperatures, you'll have different vapor pressures of water. The higher the temperature, the greater the vapor pressure. The lower the temperature, the lower the vapor pressure. But that doesn't mean that we know what that pressure is. What you would actually have to do is you would actually have to go into the scientific literature and look up what is the vapor pressure of water at 27 degrees Celsius. And when you do that, you come out with 0.035 atmosphere. Obviously, we have to look this information up. This wasn't given to us, and you're not expected to just know them. So now the question is, how do you solve for the partial pressure of hydrogen? Remember, the total pressure is equal to the sum of the partial pressures. Since we only have 2 gases present, all you have to do is subtract total pressure minus the partial pressure of water equals the partial pressure of hydrogen. So if we plug in those values, 1.043 atmosphere minus, we don't have to do any conversions, they're in the same unit, 0.035 atmosphere, we come out to the partial pressure of hydrogen, which ends up being 1.008 atmosphere. Alright, well that's your dose of Dalton's law. Let's move on to the next one. This one's called Graham's law of effusion. Yeah, I try to make it look like a race. So the main idea that I'm trying to get you to realize is this has to do with the speeds of particles, and spoiler alert, the lighter particles travel faster. So let's look at an equation. Here it is. So our equation is the rate, right, or speed of a gas. We're just going to use gas A. It doesn't matter who you assign gas A, but I do have a recommendation a little bit later. Divided by the rate, or speed, of gas B is equal to the square root of the molar mass of gas B divided by the molar mass of gas A. So notice how there's a sort of inverse square root proportionality going on here. But before we actually jump into some calculations, I just want to clarify with you. This is called Graham's law of effusion, not diffusion. Diffusion, right, is the dispersing of medium or a material through a medium in every direction kind of bit. This is not diffusion. This is effusion, which has a very specific definition. For a gas to effuse, what it means is to escape through a tiny pinhole. So let's say in this container we had all these gases, and they're just moving around super fast, colliding with each other, and they're colliding with the walls. And every now and then, a particle escapes. And they keep moving and colliding and back and forth, and then another one escapes, and another. It has to just so perfectly hit a specific position, right, or a specific place to escape a container. The rate, right, of effusion is basically how fast these particles would escape a container. So the reason that balloons will deflate over time is because inside your helium balloons, your rubber is so porous. Not so porous, but your rubber is porous, and there's tiny little holes. There's spaces for these helium atoms to fit through that every now and then they will escape. So that's effusion. All right, let's do some math work. All right, here we go. We have a problem. It says, if equal amounts of helium and argon are placed in a porous container and allowed to escape, which gas will escape faster and how much faster? All right, so we know that the fact that we're talking about gases escaping and stuff like that, this is a Graham's law problem. So rate of gas A over rate of gas B is equal to the molar mass of gas B, its inverse, divided by the molar mass of gas A. So rates, we don't know. The question doesn't tell us how fast these gases are moving. Molar masses, we can find. Helium and argon. The question is, who's gas A and who's gas B? Recommendation: make gas A the lighter gas. Alright, so between helium and argon, if you look on the periodic table, we can go ahead and get their masses. And let's go ahead and assign. So we don't know the rates. So we know that rate of gas A will be helium, because that's the smaller mass, divided by the rate of gas B, which is argon, is equal to the square root of, and we can find their molar masses on the periodic table. The molar mass of argon is 39.948, and the molar mass of helium is 4.0026. So if we go ahead and compute that, we'll get 3.1592. And guess what? That number tells us how many times this top gas travels compared to the lower gas. So we could write it like this. Helium, because that's the gas we chose, travels 3.1592 times the speed of argon. Because this number is a ratio of helium speed compared to argon speed. This is the reason that I told you to make gas A the lighter gas. The lighter gas will always be the faster gas. And in the fraction, if you put the faster gas on top, then you'll always get a number larger than 1, and it'll make sense. If you had flipped argon and helium, then you would have gotten a number less than 1, and let's just say you had done that, you would have come up with 0.3165, and it would be weird to say, argon travels 0.3165 times faster than helium, or time. It just kind of, Well, actually, no, it doesn't sound bad. It sounds okay, but the reason I want you to make gas A the lighter gas is because I want to be able to add the word faster over here. So helium travels 3.1592 times faster than argon. But if you put the heavier gas on top, then it wouldn't make sense to say argon travels 0.3165 times faster than helium. It just kind of sounds weird. So just stick with the recommendation. Make gas A the lighter gas, and then all you need to know are the molar masses of each substance. Take the fraction, take the square root, and you find out who travels faster. And well, you already know who travels faster, it's the lighter one, but if you put it on top, then you'll know by how many times. And I know what you're thinking. Gosh, that was so easy. Give me another one. No. Now we've covered all the gas laws, so I expect you to master all of them very quickly.